Let's get this centered. All right, so this video is going to be about exponential operations. They have to be fully understood in order to get to the rules of logarithms, which students typically have difficulty grasping. So we want to start that discussion from the get-go here and build off of what we talk about today. All right, so m times m times m from your pre-algebra and your algebra 1 class, you should know that's more succinctly, more simply written as m cubed. So that number 3 represents how many times m is a factor in this calculation. And if we divide m to the 3 by m, well, we can see that, you know, we'll do it with some numbers first. 5 times 5 times 5, and 25 divided by 5 is 25. And we don't have to perform that operation because division undoes multiplication. Now, this doesn't disappear, it creates the number 1. We have to keep that in mind, but 1 times that, then we don't express, no reason to. Right? And it's also important to understand that division undoes multiplication, but it doesn't have the same canceling through this addition statement. 5 plus 5 plus 5 is 15. 15 divided by 5 is 3. It's not 10, right? Or 11, however you would erroneously look at this. So division undoes multiplication, not addition in the same. I mean, you can divide 5 plus 5 divided by 5 and you get 1 plus 1. That's 2. 10 divided by 5. So it's kind of the same thing. 5 plus 5 is the same thing. It's multiplying by a fifth. So think of the division as distributed. All right, I got off topic here, but let's get back on topic. All right, but I think that needed to be said as well. The more times you talk about something, the better chance you have of understanding what you're looking at. All right, so here we have that same division creating a 1. And the rule would be, of course, m to the 3 minus, oh, sorry, I've got 2 now. All right, and 3 minus 2 is m to the 1. Well, what happens when we put another m in the denominator? According to the rule, it's m to the 3 minus 3, which is m to the 0, which represents no difference in the number of factors in the numerator or denominator. That's what that really represents. And of course, that equals 1 because we're dividing something by itself. We're going to get 1. And so this course is based on zeros and ones. We're going to use the fact that something, some base to the 0 is 1. We're going to be using that extensively as we move forward through this course. And we will, at the end of this video, plant that seed. Well, let's continue on. So we've established something to the 0 is 1. We'll hear that every single day, I'm sure. All right, so what's the rule still? The rule is you're counting how many factors there are in the numerator and denominator. And so 3 minus 4 is -1. So that -1 means there's an extra factor in the denominator in this situation. All right, and therefore 5 to the -1 is equal to a fifth. 1 more 5 in the denominator. 5 to the -2 is 1 over 5 squared, or 1 over 25. I'll write 4, 5 squared. All right. And so what does this negative sign do? Well, here it is. It's up here. And this is really 5 over 1. And it becomes 1 over 5. You can think of it as reciprocation. You can think of it as, well, let's actually do it with some numbers. See, yeah, algebra is supposed to work for all numbers. So let's look at 4/9 to the -2. Well, this is an operation. Right? And what it does is it reciprocates the base. So we've used that operation. We still have to square. And so that's 81 over 16. Squaring the numerator and squaring the denominator. So 1/2 to the x is really 1 over x to 2 over x. Right, so we have to make sure that that power is being used in the numerator and denominator. So what's another way of writing 1/2 to the -x? 2 to the x. Right? They're the same. So what was an exponential decay problem by the look of it really isn't. because that negative sign is reciprocating the base. So I wouldn't write 2/1. There's no reason to write something divided by 1. But those are true statements. All right, so we've got 2 operations so far. We've got reciprocation and squaring. I'm not going to talk about squaring. You should know that from your elementary school math. There's no need to talk about that. But what happens if I undid the squaring? Well, putting a 2 there does that, cancels it. Right? So what cancels squaring? I hope you're saying square rooting. Right? So 5 to the 1/2 is the same thing as the square root of 5. 9 to the 1/2 is 3. We want to get familiar with fractional exponents. What is meant by that? So let's do a couple of quick, you pause the video and think about what you're looking at. And we're just planting the seeds here so that we get a working knowledge. And we'll get that over the course of the semester. So you're pausing the video, 8 to the minus 2/3. Well, I think you know what 8 squared is. 64. I don't think that's a problem. I think you know what a minus sign is now. 8 to the minus 1 is 1/8. Okay, but what is 8 to the 1/3? Well, from what we just talked about before, when we had 5 to the 1/2, that 2 meant the square root of 5. That's the operation that you're asked to perform. So what happens if it's a 3? Well, I hope you're saying it's the cube root of 8. Okay, so what's the cube root of 8? 2. Right, so if we did this, I don't think order matters. Let's do it in 3 different orders. Let's do 8 squared, 64. Okay, so I've used the 2. I still have minus 1/3. Okay, so I think you understand the minus sign at this stage. So that's going to flip 64, reciprocate it, so that becomes 1/64. And we still have the 1/3, which is a cube root, and the cube root of 64, 4 times 4 is 16 times 4 is 64. So the cube root of 1/64 is 1/4. Let's do it in a different order. Let's take the cube root first. Well, the cube root of 8 is 2. What's 2 to the minus 2? Well, we know 2 squared is 4. We still got that minus operation, which is really reciprocating, so 1/4. Yeah, just getting a little practice here. So order doesn't matter. Whatever, you got 3 operations in a negative fractional exponent. 3 operations, you do them any order you want. I like to take the roots first, make the number smaller, unless it's a fraction. Then I like to reciprocate. Okay, but here you go. Well, I'm going to do the root. What's the 4th root of 16? 2, because 2 times 2 times 2 times 2 is 16. And we still have 2 to the negative 1, which is 1/2. You're pausing the video and you're trying this one. All right, well, what's the square root of 25? 5 to the negative 3. All right, so I've taken the square root, and that's 1/5 cubed, 1/125. We've got to get good at this. How do you get good at something? You do it often. All right, so we're not just going to do it for a day or two. We're not going to do 20 problems right now and then move on. Do 20 tomorrow and move on, and then really move on and see it once in a while. We're going to do this every day. It only took 2 minutes to do that. All right, so let's just do it for 2 minutes every day until we really have it. All right, now I've got logarithmic form written up here. All right, so I always like to have the sentence written. I should have probably done it before this, so I won't do it this time. Well, yeah, I guess maybe I better. All right, the exponent. You put the value of the exponent. Let me do it that way. The value of the exponent the value of the exponent. I usually have this already written and ask students to change to symbols what I'm writing. Okay, and people will always say something other than what I write. So I'm just going to cut to the chase. The value of the exponent is the operation logarithm. Now, if you read, so if you're asked to perform a logarithmic calculation, when you see the word log, you want to think the value of the exponent. That you put on top of a 5. Right? And if we do math this way, we're not getting anything accomplished because it's taking me too long to write this, right? But where do you put exponents? You put exponents on top of a base. So this is a base 5 problem. Right? So that represents the base of an exponential calculation. And normally like 5 squared is 25. Right? Normally we put the exponent on top of a base to get a quantity, but we got to get an inverse operation here. We've been doing exponential situations. What if we're solving an exponential equation? We got to have some kind of communication, symbolic communication to say that's what you're working on. All right, so this is exponent to quantity. The inverse is quantity to exponent. Okay, so the value of the exponent that you put on top of the 5 to get the quantity 25. I'm just going to put a Q here right now. Quantity 25. That would be this quantity is, which is really an equal sign, a 2. That's what's being expressed here. All right, so let's go back. A little repetition here. You perform this calculation quickly. 4 to the minus 3/2. Okay, see if you can do that. Pause the video, get an answer, and then see if you can write it in logarithmic form. Okay, I'm trying to get the exponent minus 3/2 from what? A base 4 problem that produces what quantity? All right, well, and we'll practice getting the quantity. I'm going to do that operation first, and that's a square root. I'm not cutting 4 in half. Taking the square root of 4, which is 2, to the minus 3 is 1/8. All right, so what's the exponent you put on top of a 4 to get a 1/8? It's minus 3/2. And, you know, if you're just seeing this for the first time, you're probably already lost. I'm going too fast for your brain to maybe process it. And that's okay, because I'm getting it in front of us quickly, so we have a long period of time to work with it. All right, I'm not trying to teach it in one day. In my rule of 4 in my class, we're going to do these for 4 days, and then maybe take a little longer if you're struggling with it. Maybe you're not struggling with it already. Maybe you're ready to move on. You'll be working at your own pace, but questions will be in front of you each day. And your challenge is to understand it before I have to give you a grade. All right, so how would you do this problem? Let's say you're just learning, obviously. If you're at this level, you're just learning how to do this. Well, we phrased the question. Okay, let's pretend this is an X. We didn't know that answer. All right, so how do we get that exponent? Well, first thing we do is rewrite it in exponential. We put the exponent on top of 4 to get that quantity. Well, we only have rules of exponents. The only time we can use exponential rules is if the bases are the same. 8 is not a user-friendly base of 4. I'll be careful with my language here. But I hope you can see that 4 could have been written as 2 squared to the x, and 1/8 could have been written as, I'm going to jump right to 2 to the negative 3, based on what we've talked about already in this video. All right, it's really 8 is really 2 to the 3 in the denominator, and this means in the denominator. So what's our rule of exponents here? Well, therefore that's 2 to the 2x equals 2 to the negative 3, and I think with the same base, when does 2x equal negative 3? You know, multiplication becomes division minus 3/2. Taking some poetic license here, not showing every step, just trying to get the conversation started. So we'll give you a chance to find those exponents. All right, so what's the exponent here? What's the exponent that I put on top of a 9 to get a 27? Well, let's write the exponent as x. You're always pausing the video as I go through these. Okay, what do you do next? Common base, 3 squared to the x, 3 to the 3. So therefore, 2 times x has to equal 3 because we have the same base. And so we have 3 halves. And that's mechanically getting it. Hopefully, with practice, you can either do 9 cubed, which is 81 times 9, 729, I think. And what's the square root of 729? Well, happens to be 27. Okay, but what's the way to get that without doing it in that direction is to take, oh, I just really butchered that, huh? Oh, well, the square root of 9 is 3, right? And 3 cubed is an easier way, I didn't butcher it, easier way to get that 27. So this is the exponent. That's the exponent that I put on top of that to get the quantity 27. And that's what this is asking for. It's asking for that exponent, okay? Square root of 9, you can see it now, I've written it down. Square root of 9 is 3, and 3 cubed is 27. Let's try another one. You pause the video. Almost done with this. What's the exponent that you put on top of 1 over 25 to get 125? Hopefully a month from now, you're just writing your answer without having to actually do any work. So what do we need here? I'll do it that way first. Well, I need to flip this, so I got to have a minus sign, right? Because there's a flip involved, a reciprocation. And what's the common base? It's base 5. Well, how do I turn 25 into a base 5? I need a square root. Okay. And if the square root of 25 is 5, how do I make it into a 125? Well, that's what it's got to be from a conceptual standpoint. All right, so how do we deal with it? Well, what's another way of writing 1 over 25? Pi to the negative 2. That's that. We're trying to find this exponent, so we'll call it x. And we want it to create 125, which is 5 to the 3. Writing it in the same base notation. So 5 to the minus 2x equals 5 to the 3. We're getting the conversation started, so I hope you can see minus 3 halves. Now, eventually, 2 months from now, we're going to work with this a lot to build our understanding of the rules of logarithms and to be able to graph logarithms, to be able to work with them, solving equations using logarithms. All right, this is going to take some time. Won't get it done unless we work at it a little bit every day. It's kind of like watching a ball player get a little better at soccer. You start off with what? A little push passing, a little crossing, a little this, a little that. And over the years, you don't stop. You keep doing the same things. So you get good at it. And if you get good at it, then you add a little philosophy of play. Who knows where you'll end up? Back to the beginning, b to the 0. A little repetition here. It's been 10 minutes. You might have forgotten what it is. I hope you're saying 1. Hope you understand why. We talked about no difference. B times B over B times B. That's B to the 2 minus 2. Right? I wrote 3. 2 minus 2. Which is B to the 0. You're dividing something by the same number of factors. By itself. And B to the 1. B to the 1 is B. That simple knowledge allows us to write exponential functions quickly, which is in a different video. All right, so we're going to make our exponent, first exponent, 0. All right, so you can pause the video, see if you remember how to do this, or maybe you're going to see that video after this one. Not sure what order it should be in. Not sure there's a need for order here. All right, so exponential function, exponential growth. So we got a base bigger than 1, positive base for exponential functions. Right? I'll just write it. I know all of my growth is above 7. It's all happening above exponent, quantity 7. Well, how much is 7 to 11? 4 units. It's not hard to do those first 2 steps with a little practice. Next time, I'm looking at that differential, 7 to 15, which is 8. The base of this exponential function is going to be a 2 because the second jump is not 4, it's 8. If I made this a 16, be going up a little bit faster, it would be 9. But let's go back to what it was. Let's go back to 8. Okay, that takes care of the y values. I'm just going to put a little boom, a little boom, a little boom. All right, and then we're going to turn 1980 and a 0. X minus 1980. So let's put 1980 in, see what happens. 1980 minus 1980 is 0. Anything to the 0, I'll write 8 over 4 as a 2 now. 2 to the 0, 2 to the 0 is 1. So I made 1980 become an exponent of 0, and 2 to the 0 is 1, and 1 jump of 4 plus 7 takes me to 11. And then from 1980 to 2021 is a change of 41 years. Okay, so if I change my second x to 2021, I get 41. 41 divided by 41 is 1. And then 2 to the 1 is 2, times 4 is 8, plus 7 is 15, and I got this graph. I don't need a calculator. I don't have to spend a couple $100 on that. Plus, you want to understand where these things come from. Differentials. Okay, that's you're going to get some conceptual understanding. And so the last thing I'll write over here is planting another seed. Oops, got to go this way. One last seed to plant, which won't have much meaning for you yet at all, but we're going to start the conversation. Exponential functions can be written in a new notation. E, more important than pi. E, approximately 2.71. I'm not going to say much more about it than that, than just to mention it at this point, just mentioning it, nothing else. And it turns out that if you do 2.71 to the 0.7, you get pretty darn close to the number 2. I think it's just slightly bigger than 2, slightly bigger, maybe off by 1/100 of a decimal place. But we want to get a feel for numbers, and we definitely want to get a feel for this function, e to the x, right? And I'm going to hand out a sheet early on in the semester with a few values that I think it's really important that you memorize. Right? Because these conversations have to take place over a long period of time if you're going to get a working knowledge of this discipline. Most people drop out, when they take their first year of calculus, they realize that, I think most colleges are dropping it as a requirement now because people can't do it. And people are having trouble with it so much so that it's not a prerequisite. Well, it's not a graduation requirement at the college level for a lot of institutions. And it used to be. There used to be a couple of years of calculus. But getting a feel for numbers, you'll get a feel for the discipline. So I encourage you to, you industrious, you folks out there who are ready to go after this, you learn those numbers quickly, you'll do better than those who don't. Okay. And so 1/2 to the x, a little repetition here already. What does a negative sign do? So 1/2 to the negative x. I should have put that minus sign there. I know I didn't want to. Lost track of what I was after. All right. So this flips the base, right? A minus sign flips the base. And so instead of 2.71 to something, I have 1 over 2.71. And if 2.71 gets me 2, 2.71 to the 0.7 gets me 2, then 2.71 to the negative 0.7 is going to get me, oh, God, did I butcher that? That's a 1/2. Right, I got ahead of myself here. That's a 1/3. So I apologize for that. It's the end of the video. I won't do that again. I won't do this video all over again. I'm trying to do one a day just to get a library series, as it's called, so folks can refer to different parts of the videos now with some degree of organization. So this is going to be in the exponential logarithmic camp. All right. And so I apologize for that, but here, screenshot that. I'll write something in the description of the video so that you make sure you get the correct table values. All right, so that's that. And I hope a couple of months from now, we're really diving into some of those rules of logarithms with some understanding. Because logarithms are exponents, so it's a fancy way of saying rules of exponents. All right, enough said.